Of this wonderful conference. It's a pleasure to introduce Yanki Lekili from King's College London, who will talk about a symplectic look at the Fargues something curve. Sorry.
Now? Okay. Sorry. Okay, so right, so let's start. So first I'll talk about the tutors. Okay. It's my favorite symplectic manifold. I try to run away from it, but it's I keep hitting back to it. So here's the tutors. And let me discuss a little bit about some objects of the Fukaya category in here and what we can do with them. Okay, so let me label this Lagrangian as L naught, and let me just label Ln to be slope minus n Lagrangian. So here's one which is slope minus 3. So this is L3. L naught is this one, and L infinity is this one. Okay. So here are some objects. So we can observe, we can compute intersections of two of these Lagrangians, given M1 and M naught. So they intersect at M1 minus M naught points. Okay, so say M1 is greater than M naught. So this is obvious. We can just look at the picture and see. But Floer theory makes this a bit more interesting. So instead of looking at intersections, we can look at the Floer complex. Okay. Okay, so there is a ground ring that we choose. Usually we choose Novikov ring or Novikov field. And then we form this complex. Okay. There's much more that we can do. So we can consider triangle products. So let's see. Let me just take this one. Okay, so these are three Lagrangians, three of these Lagrangians, and we count triangles. So for example, it could look like this. Okay. So let's say this is L naught, L M naught, L M1, L M2. And in this picture, these would be the inputs, and then this would be the output. Right? So we would write that as x1 goes to y times some coefficient. So this coefficient, let me write it a bit more carefully. Okay, so Where's the eraser? Oh. So it's a sum over the intersections of M0 and M2. But it's weighted by counts of holomorphic triangles, right? Such as the ones that I drew. And with a formal parameter T and the area of the triangle. Okay? So the reason that we do this is if you fix x1, x2, and y, and try to count these triangles, there are infinitely many of them. So there is you can kind of see if you look at the universal cover of this torus, all these triangles kind of unwind, and there are bigger and bigger ones like this, with the same corners. Okay, and there's that many of them, and we keep track of them by introducing a formal variable t and then the area. So this, in particular, this formal parameter t is part of this ring that we choose. And let me also say here, so this area term, the power is the area of this holomorphic curve, and this is a kind of little observation, if you like, but it's a special case of Gromov compactness. If you bound this area, there will be only finitely many triangles, right? So that's why it makes sense. And this slight variation is so if you count these triangles with their areas, usually you will get some rational numbers here, or maybe real numbers, depending on your symplectic form and the location of the Lagrangians. A nice way of modifying this is choosing a divisor. So it's a point in this case. And instead of omega u, you replace it with intersections with this divisor. Okay, so this is somehow a sort of limit of this where you think of the symplectic form concentrated around that divisor. And so then you count your triangles weighed by their intersections with this divisor. Then you get integral coefficients, so powers. Okay. So that's nice. Another observation that I want to mention is, so if I look at m comma n, say, this complex in this case is identified canonically with this complex. Okay. And let me illustrate this, why this is the case. So this is L0, and this is L2. And this is the same pattern as this one. Okay. And the reason is the identification is given by the interest around L infinity. Okay. So there's a symplectomorphism that sends this configuration to this configuration, and in general, Lm, Ln goes to. You can always apply this to interest and make this one to be L0, and then the other one will be this Ln minus m. Okay. So that's a useful identification that we have in this case, and it allows me to construct the following ring. Let me call this S. So this ring is starts with a copy of the ground field, an identity, and then direct sum of CF L0 LM. Okay. So what is the so this is the sum of all these intersections between L0 and different ones. And what's the product? So given two of these, okay, I have to give you another one of these. Well, I apply this kind of identification to replace this with LM plus n, right? And then I can apply the Floer triangle product to land into another summand of this ring. Okay, so this is the product. And a while ago, we computed this product. So it's maybe around 2009. So it's an elementary computation. But so let me just state it. So this is the small string that I can use to make this computation. So I'll integer coefficients with Laurent power series. And so the result that we obtained a while ago with temperutes is that the approach of this ring, this is a ring and it's graded by m, right? Degree m part is this m summand. So you can take the approach of this ring, and that's the projective coordinate ring of a well-known curve called the Tate curve. Okay. So this Tate curve is very easy to define. So its affine equation is as follows. It's an elliptic curve over this ring, and G2, G3 are certain elements of that ring. So they are okay. So these are both in integer coefficients power series. Okay. Okay. So, and I mean, if you're not familiar with this kind of equations, maybe there are one nice way to think about this Tate curve is you can set t equals to 0, and then what you get is a nodal curve, and this is a formal neighborhood of that nodal curve. Okay, so in the moduli space. So this kind of computation is explicit triangle computation, and in the end it gives us this important curve in algebraic geometry, and it plays a role in proving mirror symmetry over this ring. But let me maybe illustrate what kind of this kind of products, how does it look like? So I wrote here a particular case, the simplest case. So let me say x10 is CF L0 L1, right? And I want to multiply x10 with itself. Okay? And so remember, this is an element of CF L0 L1. And this is an element of CF L0 L1. In order to multiply them, I replace this. I identify this complex with CF L1, L2 using the Dane twist. And then I multiply them, right? And then I land into, so this lands into CF L0, L2. And there we have two intersection points. So let's call them x20 and x21. And what you get is the following formula. Okay. So there are integerly many triangles, and these are the number of intersections of those triangles with the base point. With corners x10, the identification of x10 with the intersection point here, and x20. Okay, and similarly with x21. So, and this kind of theorem is proven by computing all these structure coefficients between any xmk and xnk. So you just compute those. Yeah? Questions? Oh, okay. You just compute explicitly what those are, and then you match them with the corresponding computation on the algebra geometric side. So this ring that I described in the beginning has an analog on this curve, which is the sections of the line bundles over this curve. And this is the sections of this line bundles has a basis, well-known basis, the theta functions. So let's say theta mk for k 0, 1, m minus 1. So this m functions is a basis for hom OM. Okay, and this theta functions are explicit functions, so we can just read about them in Mumford's book. So they look like this. So it's a I is integer. So this is a function of two variables, t and z. T is a formal variable, but this function converges for absolute value of t less than 1, and z is an element of c star, say. Okay. So, and this matching or this theorem is proven by saying that xmk should go to, these are the intersections of L0 and Lm, should go to theta mk. Okay? And then you just multiply them here using the flirt triangles, and on the theta function side you just multiply the functions, okay, and express them in terms of the resulting basis, in terms of the basis of the result wherever it lands, and then you match these structure constants explicitly. Okay, is that clear? So, is that it's really, if you have never played with theta functions, I really encourage you to do. It's really fun. So let me just repeat. So x10 times x10 was this sum. Unfortunately, I just erased. x21, right? And what's true is if I start from theta 10, so remember theta 10 is this basic one, if I multiply this one with this one, I get exactly the same series here, and theta 2, 0. Exactly the same series, and theta 2, 1. Okay. So that's the content of this theorem. But you have to do it for all m, k, and all of the products. Okay, so far it was a review of mirror symmetry for the torus, and this is maybe the when you see this for the first time, you get really fascinated by mirror symmetry. But maybe by now we saw it so many times that it's not that surprising. So I want to introduce some new ideas. Okay. But eventually, I'll get to a theorem of this form, but it's a different kind, but of this form. So new construction. So this is the idea that we introduced in this paper called an F field. Okay. What's an F field? So when we did this Floer theory on a symplectic manifold, what's the basic thing? We have Lagrangians, they intersect, and we form a Floer complex by putting these intersections points to a vector space, by making them into a vector space and some product. So what I want to do now is, so lambda, the ring that we were using, is not going to be a ring anymore. It's going to be a field, or a field. It's going to be a field of fields. Okay, so what is it's confusing. I shouldn't have done that. Right? So field of fields, the meaning of field used in two different ways. Right? One is an algebraic field. The other one is a kind of vector field. So it's a. So we have a torus, say, or it can be any symplectic manifold. At each point of this symplectic manifold, we have a field, theta x. Okay. So this is maybe it could be maybe C, or it could be some other field, whatever it is. Okay. Field, algebraically. And then if I have two points, I have a path between them. Then there is a ring isomorphism or field isomorphism. Okay. So it's in other words, it's a local system of fields. And the idea now is use this as a coefficient in Floer theory. Okay. So here is my torus, and here is maybe some Lagrangian. Okay, so L minus 3, L naught. So CF L naught, L minus 3. By definition, it's again indexed by some x in, L3, x in L naught intersection L3, so intersection points. But now, so there are 3 of them, but they are in different locations on this manifold. So the coefficients, so instead of writing c times x here, or lambda times x here, I'll write lambda x times x. Okay. So the coefficient is here, and it's not the same as this one. It's not canonically the same. Okay. So this is a kind of a new idea that takes a bit of getting used to, but if you think about it, there is no reason to construct the Fukaya category linear over some field, right? So that's this coefficient is can be here, and when we try to prove A infinity equations, A infinity relations, wherever that coefficient is, it's going to contribute in its way, and then we're going to get the infinity equation. The proof does not see this identification of the coefficients. So I'm guessing this is not immediately clear to people, so please ask, but otherwise I'll try to explain this in terms of examples. But any questions? Yeah?
Space is path connected. You're saying that all these fields are isomorphic, just not numerically so?
That's right. Yeah, the space is connected. But, and in fact, it's a local, so if you go from here or here, it should be, if you go through paths that are homotopic, the isomorphism is going to be the same. But a priori, these coefficients are in different fields that are isomorphic, but not canonically so. And maybe more crucially, here's how I modify the product. Okay, so and I'm explaining this in this example, but of course it's a general construction. You can do this in any symplectic manifold. Remember, there was x1 here, x2 here, and then we had y as an output, and there was a coefficient of it. So now we will have x1 here, but a as well. So a is an element of the ring at that point, and b is an element of the ring at that point, at x2. And this multiplication map is not linear with respect to these coefficients. So if I know the output of product of x2 with x1, I wouldn't be able to tell you the output of every one of these. It's not linear with respect to the coefficient. So, and in fact, precisely what's the formula? The formula is like this. Y. So y is the output. Sum u, so triangles. So far the same. T to the area of u. So this is also the same. But here's the modification. Okay, and what are these things? So we have a triangle. Y is the output, x1 is the input, x2 is the input, and this is gamma 0, this is gamma 1, this is gamma 2. Okay, so we start here. So I need to compute the contribution of this triangle to coefficient of y, right? We start here with 1, and we apply this. This doesn't do anything. This just goes, because it's a ring isomorphism, right? So it goes to 1 here. But now there is an a here, so this is a. And then you apply the ring isomorphism from gamma 1 and see where it sends a to, okay? And then you apply b here. And then you apply the ring isomorphism back, and then you get what you get. So let's see some examples.
So sorry, question is probably safe, but it was a local system, so flat. It doesn't depend on the actual path, just the
Yeah. But so somehow. Yes. So it's always confusing because we are used to local systems on the Lagrangian, right? So this differs from that in two respects. One, it's ambient, as you said, and second, which is more important, is that the structure maps are not linear with respect to this. Okay, so in the usual Lagrangian philomology, when you associate the local system on the Lagrangian, it's always linear. Okay. So let's see. Let me explain what happens. So here's what's interesting. So here's the first example, and it was really this one that I wanted to get to. So here's a L0. I shifted, but it doesn't matter. Just L0. And let me equip this torus with a field of with a F field, and I will do that by drawing this line. Okay. And what this means? So let me take a field lambda. I don't know. It doesn't matter what field it is, and an automorphism sigma. But for concreteness, let's take a characteristic P field. And let's say sigma is the Frobenius. Okay, so it's a field automorphism. And this torus, so everywhere outside of this red line, I canonically identify the fibers, and it's lambda. But if you pass this, then you apply sigma. Okay, so it's a so this is what we provisionally called danger zone. But, yeah. Right. So correct. Yeah. So I want this to be a field automorphism. And in fact, soon I'll get to bigger ones, but we'll see. But here's the computation that I want to illustrate. So how do you compute philomology of L0 with itself? So you take L0 and you take a Hamiltonian displacement of it. It didn't look very Hamiltonian, but here's a Hamiltonian displacement of it. And we see two intersection points. And according to your conventions, the differential goes from one to the other one. So let's say it goes from x to y, and there are two terms. Okay? So there's this one, and then there's the other polygon. But as I explained, we have to put a coefficient in front of these guys, right? This differential is not linear with respect to that coefficient. So here, we do not intersect this danger zone, and this fiber is identified with this fiber canonically. So it's just like before. So d of ax is ay. Okay? But in this one, what happens? So we start from y. We trace this. So remember, the first one is just looking at what it does to 1. So sigma sends 1 to 1. So we pass through this danger zone, but it just sends 1 to 1. But here you multiply by a. And then you go around here, and then you apply sigma again. Okay, so what happened here is we got to sigma of a, or a to the p of y. Okay. So, question? Yeah, and t to the area, yeah, whatever. Yeah. So the important thing is this. This is now a minus a to the p of y. Right? So that's an equation that I love. Because I was looking to introduce this Frobenius into Floer theory, but I couldn't do it in any meaningful way until this. Okay, so once we see this, we can now play with it, and we can compute the triangle products, right? So in the previous example, the triangle products were interesting. Where did I write those? Okay. So there was this, it gave us this coordinate ring of the Tate curve. So let's see what it gives here, right? So I can now form this new ring, S, but using this varying field of coefficients. And now I can, so again, I'll just put some fixed lambda at identity and form this big direct sum. Yeah?
I'm sorry, I have a burning question, which is, what's the Floer homology in this?
Yeah, sorry, great question. Sorry, I meant to say that, I forgot. So yeah, so the Floer homology here is HF0 is FP, and HF1 is 0. Okay, because this thing is surjective. You can prove that. So it actually hits everyone. Well, I mean, sorry, I have to maybe I have to make this perfectoid or whatever. So yeah, let me take this lambda to be a bit bigger. So so soon I'll introduce this kind of rings, but so that's the reason that I didn't explain this until now. But anyway, so there's some big ring which has topology, and this is surjective for that in that ring, and so all the degree 1 elements die, and the fixed points of the Frobenius in that ring is Fp. Okay, so it's interesting because we have a circle, but it's not spherical, right? So it becomes a. But these ones are okay. So these are still spherical. So okay. So let me just. So I'll get back to this and explain it to everyone soon. So let me just continue with this. So I try to now compute product of xmk, a, b, x. Let me just say a x m1 k1, b x m2 k2, and then get some expansion. What time did we start? 3:30? Sorry? X m1 plus m2. There's what? Great. So, and then there's this coefficient now. Okay. Previously, it was some t powers and so on. So sorry, sum over k. So this k is 0, 1, m1 plus m2 minus 1. And then there's these coefficients which we should compute, right? So all the triangles are as before, so we know those triangles, except that every time that I count those triangles, I have to see how their boundary interacts with this danger zone. And I won't try to use this explicit formula, but I'll tell you the following. So previously, we matched this xmk with theta mk, right? And theta mk, remember theta mk was the following series. T to the m I choose 2 plus ki z mi plus k, right? And so when the F field was off, there was no these A's, and this mapped to this, and then the product of these guys were giving us these coefficients. So now what happens is we have a new thing which has this A in it, and the corresponding theta mk A is again a sum like this, but there is a sigma I to the A as a coefficient here. Okay? So you have to consider this kind of series. And this is not in Mumford anymore. Okay, so this is but this is in the book of FarguesFontaine. So FarguesFontaine introduced these series, and then the approach of this, approach of something similar to this, and so let me get to that story. So first, right. So now our theta functions got a bit more complicated. So these are all different p powers, right? But still, we can multiply them and then express them in terms of the resulting basis. But notice the basis now is not, so the basis of CF L0 Lm is not finite dimensional, right? It has this many elements, but together with the A's. For each A, we have a function. Okay, so it's not finite type anymore. Okay, so, okay. Yeah, so maybe one more illustration of what happens. So we had previously x10 times x10, and I explained it to you that if you compute this, you get this t to the d square x20 plus t to the d times d plus 1 x21. But now we modify this. We have an A here, we have a B here, and if you compute this, you get sigma d to the B, sigma minus d to the A, and sigma d plus 1 to the B, and sigma minus d A. Okay? So all of these triangles have different p power contributions. Okay? And so the structure constants of those multiplications roughly look like this. So there's some series in T, quadratic series, but some sigmas in front of them. Okay, so that's the idea of F field, and I think it's a very useful thing to consider, and hopefully other people will consider it in different settings. Next, I want to go to this FarguesFontaine curve. Okay, so now a new section, a new idea. T equals to 1. Okay, so in the previous setup, when we discussed the Tate curve, we were not allowed to set t equals to 1. Okay, the series does not converge if you set t equals to 1. When we didn't have this sigma, if I set t equals to 1, you just get a sum of z to the power integers, right? So there's no way that's going to converge anything. So, but now we have our basis, this theta mka, t equals to 1, looks a bit more, looks like you can make it converge if you use the right topology. Right? Because I don't just have sums of powers of z anymore. I have in front of it, there is this coefficient, which can, if I put a topology here, such that this kind of converges and dominates this term, then it can converge. Yeah?
So in the first story you told, like the classical story, T was the element of lambda.
Yeah, but it also, everything converged if the absolute value of t is less than 1. You could set t to be...
You think of T as a number.
Yeah, you could set t as a
So
number.
now, in this second story, is T supposed to be a number, or is it an element of this local system of fields?
No, local system of fields is this part.
So T is not, the symbol T doesn't represent something.
T is a formal variable, okay? And you could set t equals to 0 or t anything that has absolute value less than 1, and then you'll have convergence as before. But the observation here is that you could also set t equals to 1 now. Okay, so we are in a different limit of this thing, which didn't exist before. Okay, and the reason that we can is because if I choose A to be in the maximal ideal of this ring, such that this goes to 0, then I can make sense of convergence of this. In fact, so let me write the ring where this takes value. So this is a ring that was introduced by FarguesFontaine. So it's a series of the following form. And AN is in this lambda. But lambda is this. Lambda is now this topological ring with a non-discrete valuation. But anyway, so let me not write that. Such that AN R to the n goes to 0 for all R in 0, 1, and n goes to infinity. Okay, so there is a ring like this. It's an everything is convergent here. There is no formal parameters, and these theta series are elements of this ring. Okay, and you can multiply inside this ring. Okay, so okay.
So, what do you, I mean, you predict A, so you keep saying this thing that, like, it's, the operators are not linear over the local system of fields. But this homomorphism of sigma does have a subfield that's fixed.
Correct.
And so
Which is FP.
What's that?
Which is FP,
Which is FP.
and it's linear over FP.
Right.
But this thing is infinite type over FP. So
Right. So, but are you saying something like you're not allowed to use that A here? Because, I mean, if you use that A, then
you
all
can
of these-
you can use that A, and this will be just constant.
Uh-huh.
But there's more A's.
But would it still converge when it's
Yeah.
constant?
Oh no, so right. So it won't converge because that will not be in the maximal ideal.
That's a good issue.
Yeah, that's right.
Good issue.
So we have a field, and it has a max. So it has a valuation, and these are the elements. Sorry, these are the elements whose valuation is less than 1. Okay, and then there is a identity times FP is the other ones. Okay. Okay, so let me state the first theorem. And then I want to explain a little bit more Floer theory. So the first term is proj of this ring equals to 1 is the homogeneous coordinate, is the projective coordinate ring of this of FarguesFontaine. Okay. One way to say that directly is actually there is a description of this FarguesFontaine curve which uses this these theta functions as bases of the string. So that's kind of a tautological way of defining this, but there's still a theorem here, because what it says is that if you compute these products with Floer triangles, that matches with computation of the products of these theta functions within the string, right? So, okay. And there are things to explain about this, this curve. So maybe I can give you some information about that. So it's a, so this is a, this I'll call x of lambda. So this x of lambda is, so it's a regular Noetherian ring, Noetherian one-dimensional scheme. But it's not finite type, right? So it's over F, it's one-dimensional, but somehow it's not finite type over any field. So it's linear over FP, but it's not finite type, and I explained why. So it's these A's, but it's still nice. So and one interesting property is that the arithmetic genus is 0, so H1 of O is 0, and that's the computation we did, right? So that's the Floer homology of L0 with itself. CF1 was 0, and so this is CF1 is 0. Okay. So why do people care about this? So somehow this is a very fundamental thing in the periodic Hodge theory or periodic geometry. I don't want to somehow, it's a long story, I don't want to go into that direction, but maybe I can say that one can express the Ram comparison theorem so this is Faltings and more recently Scholze and FarguesFontaine as in terms of vector bundles on this curve. Okay, so this is a we all learn in when we in grad school that there is Hodge to de Rham degeneration, so over complex numbers. So we have Hodge cohomology and de Rham cohomology. They are isomorphic. So and then there is a periodic analog of that. So you learn that in grad school if you study number theory. I didn't. But so now I'm a big fan. So there is a Hodge to de Rham degeneration in the periodic world as well, but it's much more complicated. But in the end, there's the natural way to study those is in terms of vector bundles on this curve. And there's a classification of stable vector bundles on this curve, and they are given by semi-stable on XE are of the form O of a rational number. Okay. So just like a Grothendieck's theorem about vector bundles on P1 is O of an integer, like sums of these guys. So these objects are the analogs of O of n on P1, and mirror symmetry explains this as well very nicely, right? If you have something that's parameterized by rational numbers, you should think of Lagrangians, which are parameterized by rational numbers on the torus. So these are the mirrors to those guys. Okay, so and then there is a final bit of the story that that I want to explain, which I didn't. I kind of hid from you. What is what? E. Oh yeah, sorry. It's lambda. Yeah, it's sorry. I should have written E from the beginning, but anyway. So But thanks, that's exactly what I was going to talk about. So if I take x of this O of lambda, for this curve, what I get is not fp. So it's not fp. Remember, we did this computation and we got fp, right? So everything works except this particular cohomology group so far. And what is it? It's more like fp. Well, adjoint z or maybe fp z inverse. Okay. So this curve is Hom. Yeah. Sorry, Hom. Yeah. So x1 is 0. But it's actually a curve over not just fp, it's curve over something bigger. Okay, so that's it's bigger. It's exactly that one. Yeah? So what it means is that this there should be an action of z on the other ones. Right? So this is so if I have L0 and Li, right? Hom L0 Li is a module over Hom L0 L0, right? And Hom L0 L0, it was just this intersection point, right? And in fact, the cohomology, it was just fp, and we can just multiply it using the Floer triangle to make it into a module. But where is the z action? Yeah.
The Floer cohomology calculation gave us fp.
Yeah.
But now are you saying that the FarguesFontaine curve, that's not the correct answer for the FarguesFontaine?
Yeah, it's bigger.
So the correct answer for the FarguesFontaine curve is the bigger one.
Yeah, either this one or this one. Okay, so that now I'm gonna fix the problem. Okay. So, and I'm explaining what's the difference. The difference between being over fp or over this means you should just have an action of z. And here's the fix. So 5 more minutes, right? Yeah. So first we notice the following. So this is L naught, and this is L naught push off. Okay, they don't touch each other, and I have the danger zone here. And if I compute the Floer homology, this is 0. Okay, but now let's apply Hamiltonian isotopy of L naught tilde. Okay. So now it intersects. Okay, and we can do the previous computation. And what we get is fp, right? Just n degree 0. Because there's 2 disks, and d of ax is a minus ap y. So why did that happen? Because I set t equals to 1, right? So if I didn't set t equals to 1, then what would happen is I would get something which is invertible in the Novikov ring, and then it would again give me 0 cohomology. But I set t equals to 1, so I lost Hamiltonian isotope invariance. Okay? So therefore, in fact, this is not the right thing to do. So I have to modify the definition of Floer homology of L0 with itself. And here's the modification. So the reason that this issue arises is because of this annulus between L0 and L0 tilde. So if I try to write this continuation map that will give this isomorphism, the continuation map has infinitely many terms corresponding to this holomorphic annuli, and they don't converge at t equals to 1. Okay? So I have to remove these annuli. Okay? And the way to remove, so of course, you can do this. You removed one of the annuli, but there are actually infinitely many annuli. Right? So if you think of this picture, so these are two things. There's one annulus here, which I remove by this isotopy, but then there's this one as well. Right? There's infinitely many annuli. So I have to remove all of them by this isotopy. So we coined a term for this. We call it loud phleromology. Okay? What it means is that we apply, so we take this one, and then we increase the volume of the, by doing this, right? So let me just try to do this like this. So this is the first perturbation. But then we increase it again, like this, like this. Okay, this is the second iteration. And then we increase it again and again and again, and we take a limit of these things. And that's the, so that's actually a very similar thing appears in Hederley's thesis for the purpose of some gluing. But this is in a close, somehow different setting. So we have this phi m of L0, which is the Hamiltonian flow of a cosine function on the torus. Okay? And we take the colimit. And that gives you a complex. And what happens, observe, is each time you create new intersection points, but also new two disks. And one of them is intersects the danger zone, and the other one doesn't. So each time you take this kind of limit, this iteration, you're introducing a new FP. Okay? So what happens is then this, you can check and compute that this is isomorphic to FP C Z inverse. Okay? So it's the right answer. So whenever there's annuli, so this is a very different, so maybe not to confuse you. So there's two different issues happening here. One is we are using this F field to twist the coefficients, right? So somehow we don't have a linearity. There's this interesting FP Frobenius happening. But the other thing that we are happening here is that by setting t equals to 1, we lose Hamiltonian. So somehow we have to, we set t equals to 1, and then there is convergence issue. And this convergence issue is due to the existence of holomorphic annuli. And these, by perturbing and removing those annuli, you get around this convergence issue, and then you get a Hamiltonian invariant theory, and it also gives the right answer. Okay, so that's it.